Hey guys, today we're going to learn about Planck problems, which is a classic set of problems in physics, and it has to do with torque, so this is the right time to do it. They call them Planck problems because this is a pretty typical example of it. You have a plank laid across two sawhorses here, and a cat is walking out toward the end. And one question that could be asked is, well, how far can the cat go before it tips the whole plank and dumps it on the floor? And you got to know the mass of the cat and the mass of the plank and where the sawhorses are and all that stuff, and you can figure it out. Another version of the problem is, okay, the cat's standing here, the plank weighs so much. How much weight is each sawhorse supporting? That's another type of Planck problem. Okay, now to do these, we have to review the concept of equilibrium. You remember this one. An object is in equilibrium when the net force acting on it is zero. So if the net force acting on an object is zero, that means that it is not accelerating. So an object in equilibrium either is moving at constant velocity or it's not moving at all. But today I put a little asterisk on this one because we learned about another kind of force, which is torque. So we also have to take into account that the net torque is also zero. So an object which is in equilibrium is not accelerating in a straight line, nor is it changing its rotation. Now, the torque lab that we did yesterday, we had a balanced beam with weights hanging off of it, and we always tried to get it in equilibrium, which meant that the linear forces were balanced and the rotational forces were balanced. And that concept is what we're going to be able to use to solve Planck problems. Okay, so where we're going to start here is with this problem here. And the students that were in class last time saw this, but those of you at home, it may be new to you. So here it is. Okay, so we have a stick just like we used in the torque lab, but it's not hanging from the center. When we did the torque lab, we hung the beam, the meter stick, from the middle so that it balanced and we could ignore it. We could ignore the mass of the stick because the only thing that added to the torque was the weights that we hung in different places. But today, I don't have the stick hanging from the center. So now the weight of the stick itself matters. So this is 430 grams, and it's hanging from the first hole. And the whole contraption is hanging from the second hole. And it all balances. So again, our challenge is to figure out what is the weight of the stick. The mass of the stick is what we're trying to find. It's a meter stick. It's hanging from the second hole. We have 430 grams hanging from the first hole. Now, I'm going to pause this twice here, and I want you to pause it pretty much right now to see if you can figure this out yourself, okay? It's an interesting problem, and you may be able to do it entirely on your own. So pause the video now and give it a try. When we start it up again, I'll give you a hint to maybe get you unstuck, and then we'll pause it again. Okay, so pause it now. Okay, now you're back, I assume. So the hint here is that the stick itself behaves as if all of its mass were at the center of the stick. Okay, so this is the mass of the stick. It behaves as it's a stick with no mass with a weight hanging from the center of gravity of the stick. Now, during the, excuse me, during the torque lab, we hung the stick from this point so that all the mass was hanging right underneath the suspension point and it provided no torque. Okay, so treat the stick as if all of its mass was at this point. Pause it again, see if that'll get you where you're going to go. Okay, we're back, and let's see if you got the right answer or see if we can get you unstuck here. All right, so as we know, torque is equal to force times distance, and the torque on this side of the pivot point has to be equal to the torque on this side. So we're going to set those equal to each other. So the torque making the stick rotate this way is the mass times 0.3 meters because it is 3 holes out from the suspension point. So it's m times 0.3 meters. That describes this torque, the torque that direction. And the torque on this side is 430 grams times 0.1 meter because it's 1 hole out, and that's all the torque that's on this side. And now we just solve for m. So we have 430 times 0.1. We're going to divide that by 0.3, and we get M is equal to 143.3 grams. Great. Okay, now I'm going to show you another way to do it. And this leads us into the Planck problem. So that's why I had you start with this one, okay? Because it is in equilibrium, it turns out that we can pretend that it could rotate from any position. Now, we used this position as our reference point for this problem because that's where it actually would pivot in the real world. But since it's not pivoting, since it's in equilibrium, we can pretend, for example, that this could be the center of rotation. That if the forces on it were not balanced, the forces and the torques were not balanced, that this is the point where it would rotate, okay? So now we're going to solve it again with the assumption that this, the end of the stick, is where it would rotate. And again, we have to set the torques equal to each other because there's some forces which are causing it to try to go this way, and there are other forces that are trying to make it go this way. All right, so let's deal with the downward forces first, okay? So we have the mass of the stick. We don't know what that is, but we know that it is half a meter from our pivot point, okay? Because it's the middle of the stick, so that's going to be times 0.5 meters. And I apologize for using M for two things, but yeah, this is the mass of the stick, half a meter from our pivot point. Okay, the other force that is trying to make the thing swing down is the 430 grams. So we have to add the torque in for that, 430 grams, and that is 9 holes out, which is 0.9 meters times 0.9 meters. And that's all of the forces which are trying to make this thing spin clockwise, which technically is a negative torque. All right, now, so what's keeping it from swinging down to the floor? Well, the stick is being pulled upward by the suspension point, okay? That string that we hung it from is pulling it upward toward the ceiling. It's counteracting the force of gravity, right? Since the thing is in equilibrium, it's not just the torques that are in balance, it's also the weight, gravity pulling it down, and the tension of the string that's holding it up. So that means they have to be equal to each other. So what is this upward force? Well, it's 430 grams, this, plus the weight of the stick. So that's plus M. That's how much force is pulling this thing up. Now we're keeping it in grams just to keep the math simple. To be perfectly proper, we should transform it into newtons. But for our purposes, we just want to know this mass so we can keep the numbers in terms of mass. If we convert it to newtons, we'd multiply these by 9.8. We'd get an answer in newtons, and then we'd divide that answer by 9.8, and we'd come back to mass. So why not just skip that and keep it in grams? It works fine for this problem. Anyway, so that means that the torque trying to make it rise is 430 plus M times 0.8 meters, because it's 8 holes out from our imaginary pivot point. 1, 2, 3, 4, 5, 6, 7, 8. So that's the torque. So that's the torque that's trying to make it go up. This is the torque that's trying to make it come down, and they have to be equal to each other. And now we just solve for M. So we get 430 times 0.8, so we get 344 times 0.8 M. Distributing that is equal to 0.5 M plus 430 times 0.9, which is equal to 387. And we wind up with well, I'm going to do it over here because I need to do something more. So 0.3 M is equal to 387 minus 344 is equal to 43. Divide 43 by 0.3, and we get 143.3, just like we did before. So M is equal to 143.3 grams. So it works either way. All right. Now, I would like you to pause it in a moment here. I want you to practice this idea by using this end as the imaginary pivot point. Okay, so with this end as the imaginary pivot point, we have the 430 grams. It's only 0.1 meters away, trying to swing it down. And then the weight of the stick, half a meter away, trying to swing it down. And countering that is the upward force, 430 plus m, only 0.2 meters away. And if you do it right, you should come out with the same answer. Okay, so pause it, come back, and we will, well, I'll show it to you. So it'll be here when you come back. But pause it, try to solve that problem, and then we'll see it. Okay?